Okay, I will be discussing today worksheet number 1 from Unit 3. So the first question asks about the different types of energy storage. This is something that we learned in that reading from a few days ago. So thermal energy is stored in the movement of particles. Movement, this is something that we learned in Unit 2. So thermal energy is essentially the temperature of the particles. Temperature is measuring how much thermal energy they have. So faster moving particles have more thermal energy and a higher temperature. Phase energy is stored in the arrangement of particles. This is one that's newer to us. So by arrangement, I mean, is it a solid, liquid, or gas? We talked about how there's attractions between particles. Those are called intermolecular forces. And in a solid, those attractions hold them into a rigid shape. In a liquid, there's more energy, so they're able to overcome those attractions and slide around. And then in a gas, they've overcome the attractions completely, and they can fly apart and not be attracted to any other particles anymore. So that's what we mean by the arrangement of particles. And then finally, chemical energy is stored in the chemical bonds between particles that are in the particles. And that is something that we will not discuss in depth until second semester. So for now, you just need to know the definition. But when a chemical reaction happens, that's when the chemical energy changes, and we will revisit that in a future unit. Now here, we're just going to go over what happened in the Icy Hot Lab. So we saw that at the beginning of the lab, and I'm going to do this slightly above the 0 degrees so we can see it, the temperature did not change for several minutes. And then the temperature went up quite quickly. There was a steep line. The temperature increased quite quickly. Forgot to label this temperature on the side. And it increased until it got to the boiling point, 100 degrees, and then it started to boil. And when it boiled, then the temperature leveled off again. So it looked like that. There were 3 regions. So our 3 regions, I'll separate them with a line here, are like this. So this is region 1, this is region 2, and this is region 3. So in region 1, when we first put the ice was melting. And the ice was melting, which means it was turning from a solid into a liquid. So there was a combination of the two. Sometimes people make a mistake. They tell me it was just a solid here, but it wasn't, because it started as a solid, it turned into a liquid. It was like a mixture of ice and water until the very end, where the last little bit of ice melted. So in our particle diagram, we need to have some particles arranged like a solid. So we'll do that with vibrating lines to show they're a solid. And then since there's a liquid too, we'll have some particles in there that are they're pretty slow moving. I'll put kind of a mixture. Well, we'll do 2 for all of them. Liquid particles with the solid particles. So there was some ice and some water. And so during this whole period, the ice melted, but notice the temperature did not change. So the movement of the particles did not change. Any energy we put in at this point was rearranging the particles. It was stored in phase energy. So this is phase energy. We know phase energy is happening because the temperature does not change, and with our eyes we saw that there was a phase change. Now in region 2, this was after the ice finished melting. A common mistake on this one is to tell me the ice is still here in region 2. It is not. All the ice melted in region 1. The temperature did not start going up until the ice was gone. So here it was just liquid water, and the liquid water was heating up. Its temperature was increasing. So it was kind of boring to look at. That was just liquid water sitting there getting hotter, and it was only a liquid present. And since I gave 2 swooshies here, I probably should have done 1 there, but I wasn't really thinking. So I'm going to do 3 swooshies here to show that it is warmer. And I guess 4, 7, 1, 2, 3, 4, 5. 7. Got to be consistent, right? Although there was a little bit of evaporation, but the majority of the water was just staying as water. And now, since the temperature is increasing, we know the thermal energy is increasing because temperature is correlated with thermal energy, which means this was thermal energy, ETH, that was increasing and changing. And there was no phase change, so no phase energy. Then finally, at 100 degrees, the water was boiling. And it didn't just boil all at once. It was a combination of liquid and gas. Some of it was still liquid, some of it was gas. So in our picture here, we'll have some very hot liquid particles. Get 4 swooshies. And we'll also have some very hot gas particles. And so because there is a phase change, liquid to gas, but also because the temperature was not changing here, we know it was phase energy. So anytime on a graph like this that it is flat and there's no temperature change, you know there's a phase change, and it's phase energy that is changing. And anytime the temperature changes, you know that there is no phase change and it's the thermal energy that's changing. All right, so going to the back. This first question is asking what I just said. How can we tell if it's changing? So just to reiterate, flat is a phase change because there's no temperature change. And if the temperature changes in some way, in this case it was increasing, but in a cooling curve it would decrease, that means it is thermal energy. Oh, and phase change, of course, is phase energy. All right, now this one, we are going to apply what we know to a new situation. So it says that this is showing the cooling curve. Cooling curve, of course, is the opposite of a heating curve. Instead of adding energy, we're removing energy from the system. Otherwise, it's pretty similar. And it's saying as it freezes. Now that is a phase change. Freezing is going from liquid to solid. And we know phase changes happen when there's no temperature change. So if we want to divide this up, this flat part in the middle, that's going to be where it freezes. And if it freezes there, that means it's going from a liquid to a solid. Now, right before something freezes, it is a liquid. And right after something freezes, it is a solid. So liquid, liquid and solid, and a solid. So that's B for labeling the phases. I'll do the A in a moment. Let's do the particle diagrams first. So the first one's just a liquid, but it's a pretty cold liquid. It's about to freeze. So I'll just do like one swooshie on each of those. And then when it's freezing, it's a combination. So I'll do a couple sort of solid ones. I'll do one more particle here so I have more to work with. So we have like a combination, some solid, some liquid. And then finally, it's just a solid at the end. So we have just a solid there. I guess since these have one sushi, I should make these a little warmer, huh? All right. Then finally, the second part, which was actually A, said sketch the curve for a larger sample of the same substance. So if you have more, it's going to have the same freezing point. So it should be at the same general like point in the y-axis of the graph. But if you imagine putting a small amount of, say, water in the freezer versus a large amount, like a tiny thimble versus like a big water bottle, the small amount is going to freeze faster because there's fewer particles to remove the energy from. So our large amount is going to be the same general thing, but just kind of stretched out because it will take more time. We have to remove more energy from it. So we'll just stretch out the cooling time, stretch out the freezing time, and stretch out the cooling time here. So it just takes more time. All right, and then last but not least, it talks about isopropyl alcohol has a melting point of negative 89 degrees Celsius and a boiling point of 83. Draw a heating curve and use the entire range of temperatures. So this heating curve is going to look a lot like water. The difference will be where the phase changes happen. So our melting point is down here, negative 89 degrees Celsius. Our boiling point is up here. It's 83 degrees Celsius. So, and this is starting below the freezing point. So as we discussed in class, this is like very cold frozen alcohol, and it needs to heat up to its melting point before it can melt. And then at its melting point, it will melt. And then once it has completed melting, it will heat up to its boiling point up here to 83 degrees. Once it reaches its boiling point, it will boil. And then once it finishes boiling, if we keep heating up the vapor will continue heating. So it says label which phase is present in each section. So it starts as a solid, the very cold solid that gets heated up to its melting point. Here it's flat because it's melting, and that's going to be a combination of solid and liquid because it is melting. So it's not ice, it's frozen alcohol, but it's that combination of frozen solid alcohol and liquid alcohol. Then here it is a liquid that is heating. And then finally, when it reaches its boiling point, or not quite finally, second to last, when it reaches its boiling point, it will be a combination of liquid and gas because it's boiling. And then after it boils and it finishes boiling, it will just be gas and will heat up, which is often called vapor, like water vapor, alcohol vapor. And it did not ask necessarily what sort of energy was being produced or used or stored, but I will write that anyways. So over here it was ETH because it was heating. Here it's EPH because it's a phase change. Here it's ETH again because it's heating again. Here it's EPH again because it's a phase change. And then here it's ETH because it's heating. Remember, whenever it's flat, it's a phase change. Whenever the temperature is increasing or decreasing, as it was up here. In fact, let's label those two. So this is ETH, this is EPH, and this is ETH. All right, hope you found that helpful. Have a great day.